Okay, we're going to be studying this. This is a 16-1B video. We're going to be studying speed of a wave on a string. And we're going to look at the different characteristics of that string that would cause the speed to change. So I'd like you to think right now, take a pause of this video, and think right now what characteristics of a string might cause the speed going down the string to be different. Here we have a string that's connected to a plunger that moves up and down to cause a wave to go along a string. You'll see that right here. And it takes about 1.5 seconds for the string to get down to the other end. I'll move back here a little bit and we will see it's about 1.5 seconds. And then what I want to do is change a few things about this string. What I'd like to do is change the amplitude of this, and we'll put it up here and see how long it takes for the wave to get down the string. In this case, it still takes 1.5 seconds, even though we've increased the amplitude. The amplitude did not change the speed of the wave. Well, let's try the frequency that we move the string with. The frequency here now is 3 hertz instead of 2 hertz. We now have a more frequent wave, and we also see that it takes about, if I go back here to the beginning, it's about 1.5 seconds. Let me reset this, hold on. We're going to try that again. And stop it right before it hits. And you'll see if you go one more step forward, it's 1.5 seconds again. So the frequency of the wave did not change the speed of the wave. Let's go ahead and set the string thickness to a different spot. We'll make it a heavier string. We'll play this now. And you'll see the wave is moving more slowly. You can think of it as a big, heavy rope that would cause the string to move more slowly. And so it's about 2 seconds for that wave to get down to the other end. So if you make the string heavier, and if you change its linear density, it will then move more slowly. So that's one of the characteristics. And you could think about, if you take a nice thin string and send a wave down it, and then a big, thick, heavy rope and send a wave down it, you know that the wave travels slower in that big, heavy rope. It's harder to move that rope up and down. You'll also notice in this video here that this red dot right there is part of the string, and this is not part of the equation, but this is just one important feature of a transverse wave, is that the red dot simply moves up and down. It does not move forwards and backwards. In a transverse wave, the string itself moves up and down. The equation for a force for the velocity of a wave down a string is this. It's the square root of the force of tension divided by mass per unit length. The V is the velocity of the wave. The F is the force of tension that's on the string, and that also will change. If you pull on that, that also will change the velocity on the string. If you pull on the string more tightly, the wave will travel faster down the string. So it not only depends on this linear density, this mass per unit length of the string, but also the force of tension on the string. This M per L, this mass per length, is the linear density of the string. It's the mass of the string divided by the length of the string. In some of our physics problems, they'll give you the mass per unit length of the string, or they'll give you separately the mass of the string and then the length of the string, and you'll have to calculate the M over L, the linear density of that string. So here's a problem that we're going to do. If you'd like to pause the video and try this on your own, I would suggest that you try this before I show you the answers. Transverse waves travel on the strings of an electric guitar after the strings are plucked. The length of each string between its two fixed ends is 0.628 meters, and the mass is 0.208 grams, which we have to convert to kilograms. For the highest pitched E string, and 3.32 grams, which again we have to convert to kilograms for the lowest pitched E string. Each string is under a tension of 226 newtons. Find the speeds of the waves of the strings. So we're going to use our equation that we just looked at, and if we plug in our values to that equation, we get this. Both cases the force was 226 newtons. Remember, you had to change the mass to kilograms, and the length was 0.628 meters in each case. For the high-pitched D, the wave traveled down the string at 826 meters per second. The low-pitched D was 207 meters per second. One thing I need to point out is that the speed of sound is not what you're calculating. You're calculating here the speed of the wave traveling along the string. The speed of sound is very different. The speed of sound, or how fast the air molecules bounce into each other, how fast sound travels throughout the air. So how fast the wave travels down the string has nothing to do with how fast the sound travels in the air. And at room temperature, the speed of sound in air is 343 meters per second, whether you have a high pitch D or a low pitch D. Here's a conceptual example I'd like to look at, the wave speed versus the particle speed. There's even another speed that we're going to talk about. It's actually the speed of the particle. So we have the speed that the wave travels from left to right in this picture. You see the speed of the wave right there. The arrow shows that the wave is traveling down the string to the right. But there's also a velocity of the particle moving up and down. I'd like you to pause this video and think about what that velocity is like and what kind of motion is occurring. Is it a linear motion or is it some other motion? I'd like you to think about that. Here we have, we'll just read this first question. Is the speed of a transverse wave on a string the same as the speed at which a particle on the string moves? And after you thought about it, hopefully you realize it's no. And as a matter of fact, if you read this down here below, it says a transverse wave on a string is moving to the right with a constant speed of v sub wave. A string particle moves up and down in simple harmonic motion with the undisturbed position of the string, or about the undisturbed position of the string. The speed of the particle, v sub particle, changes from moment to moment as the wave passes. It's in simple harmonic motion, so its maximum velocity is here in the middle, and its velocity at this end, or the velocity at that end, down here, is zero. It actually stops for an instant. So it's in simple harmonic motion, and the velocity is constantly changing. Maximum velocity being in the middle, zero velocity being at the ends. And here is this. This just describes what we just said. So you're going to have to know the difference between these three velocities. It can be somewhat confusing. You can have a velocity down the string, which is typically constant unless the string itself changes. You can have the velocity of the particle moving up and down on the string, which is simple harmonic motion. And you can have the velocity of sound that travels throughout the air due to that vibrating string.